Labdien, ladies and gentlemen. I learned one word in your language. Unfortunately, I cannot speak your language. Я понимаю по-русски, но я не говорю. Я говорю только немножко. So I will speak in English today. Hopefully, it will be okay with you. My presentation, can you switch it on, please? Thank you. I'm from the same company, IDEA RS, from Czech Republic. This is a country in the center of Europe. You might have visited it. If not, then please do it. It's quite nice to visit Prague. I hope I see a bit of Riga today. So I will be speaking about the Eurocode design of reinforced and pre-stressed concrete structures. I will start with this hierarchy of Eurocode. I noticed that Gatis already mentioned it. We have safety and durability concept given in 1990 Eurocode, then some loads in a group of Eurocodes 1991, and then there is a group of Eurocodes for structural design. One is EN 1992, which is for concrete. I'm sorry for this. This is probably because of the software, and we have different version of PowerPoint in our company, so sorry about it. I will be speaking mainly about this EN 1992-11, which is the general Eurocode for concrete, but we have implemented also structural fire design, concrete bridges and liquid retaining and containment structures. Those are Eurocodes for concrete and pre-stressed concrete. I will start with the materials, some interesting features which you should know. And it is about modulus of elasticity. Everybody knows this parameter. It is very interesting, and we learned in the school that it is a tangent of this first branch of stress-strain relationship. You can see here strain at this point, and if we go further, this one is additional, different value, different relationship. And if we go to the table, which is given in Eurocode, we see that these two are constant. What does it mean? It means that if you have cube strength or FCK, this is cylinder strength variable for different grades of concrete, then, and this is constant, then you cannot match these values of modulus of elasticity. So the modulus of elasticity, which you calculate for ultimate limit states, is from relationships, stress-strain relationship, is completely different than the stress-strain relationship which is in the table, which makes it a little bit tricky, and we had to appreciate it in the calculation. Some other interesting features on modulus of elasticity. We know that there is some formula in Eurocode between the relation between strength and the modulus of elasticity. Which is actually the second value between those two values of stress in concrete. But this is valid only for quartzite aggregates. If you have, for example, sandstone on basalt, it could be -30 and +20%, which means it is very sensitive to local materials. And we experienced it in our country that it really was. By the way, there is also tangent modulus defined in Eurocode, which is 5% higher, and it should be used when you calculate the creep factor and calculate creep effects. Now I go to, that's unpleasant. This is reformatting of, doesn't matter, I can show it. Sorry about that. This is the problem of this reformatting. I didn't go through the whole PowerPoint presentation. That's pity, but doesn't matter. I will explain it what I wanted to show in this picture. The second table was SNP. The first table, which is not visible now, was Eurocode and the comparison of moduli of elasticity between Eurocode and mother of Eurocode, which was CEB FIP code 1990, and also model code 2010. Those are international codes, and Eurocode takes the methods and parameters from there. it is interesting that moduli of elasticity are about 15% higher than the moduli of elasticity in those model codes, which is very strange. And I wanted to show that in SNP, there is a similar value of moduli of elasticity as it is in Eurocode. But you probably know better than me that it is not used for the calculation of deformation of concrete. For example.
Sorry.
We made it intentionally to wake you up. So we are sorry for it, but on the other hand, something is happening and it's good, always good. Coming back, I said that SNP and Eurocode, they have similar level of moduli of elasticity, but what I wanted to say, for the calculation of deformation, they use for short-term loads 85% of the moduli of elasticity only. So this is the 15% I mentioned before. But there is no such factor in Eurocode. Be careful about it. It was a problem in our country, and there were some, I would say, contributions from the practice to university professors and to the Eurocode people that usually when you produce the concrete, at least in our country, the modulus of elasticity was lower than the one which was calculated according to Eurocode. So for in SNP code, you have even the decreased these reductions because of the service conditions. And I do recommend this determination by tests in case that you have a structure sensitive for the deflections, or crack width. So this is one property which I wanted to mention. The other one is that there is no limit strain in a steel stress-strain relationship in case that you have a constant plastic branch of stress-strain relationship. You see, this is a SNP. We have limit values, but here we do not have. Practically, it means that if you have ultimate limit state of the section, you cannot get the reinforcement breakdown. So only the ultimate limit state can be reached only by crushing of concrete. Of course, in case that you have inclined branch of this stress-strain relationship, then you have this limit strain. This is a picture, unfortunately unformatted, of the dependence of the modulus of elasticity on age of concrete. Eurocode gives you the formulas for slowly hardening, normal hardening, and rapid hardening concrete, and these formulas can be used for the calculation of changes of modulus of elasticity. If I remember, in SNP you had only some tables and factors. Similarly with concrete, there is quite a sophisticated method and model for creep, especially for Eurocode for bridges, which is 1992-2. The concrete creep is calculated by this formula in case you have variable stress, and you have always the variable stress, but you have to respect the history of loading, and the creep function is such that the creep history can affect the value of the creep. Similarly, superposition principle. Actually, this history of loading together with principle of superposition gives you this formula. When we go to the checks, to assessment of the sections, we have the ultimate limit state in flexure, and this ultimate limit state is calculated based on a stress-strain relationship. Actually, stress in every fiber is analyzed in each fiber of the cross-section in each bar, and then you have to guarantee the equilibrium conditions. So if we have such forces applied on the section, then we can calculate this distribution of stresses. Here in this part you can see the plastic part of the concrete, and then We are on a linear branch here. This is strain and stress in the rebars, reinforcement bars. Those are the pictures from our program, which we can discuss later. This ultimate limit state is based, and I think Gatis already mentioned it, based on equilibrium and strain compatibility. What you can see in the program is that you have the distribution of strain in the cross-section. We call it, during socialism, we call it Navier hypothesis. They call it Bernoulli hypothesis in the West. So I call it Navier by Bernoulli hypothesis. But it was actually discovered by Robert Hooke, if you don't know. It was earlier than those two guys. And when you calculate the stress based on this strain, and you will see this parabolic rectangular relationship in the concrete in compression. Here the different color means that we are on plastic branch. Here we have linear branch of steel, and here we have plastic branch in steel. The new SNP, this one, has similar approach, so it should not be very different for you. About shear resistance. Shear resistance, we have members without shear reinforcement and members with shear reinforcement, which we will speak in later. Now we will concentrate on these members without shear reinforcement. We have two methods in Eurocode. One is for correct sections. This is based on more Coulomb shear friction theory, and this one is based on linear elastic analysis. That's quite simple. You can derive the formula by hands. But the problem is that those two approaches give you completely different value. For example, this, if you have such simple structure, and this is your shear force, then assuming that at the beginning you have zero or very small bending moment, there are no cracks. So you can use the second formula, which is for elastic analysis. But when you use the second one, the first one, which is for cracked section, you drop from almost 90 to 50. So it is almost double. The difference is almost twice. So in that case, you can get this part of the beam, which you do not cover by your resistance. So be careful about it. It is not enough if you check it at the end of the section. You should also find the critical section related to the section which is cracked. Now we go to equilibrium conditions, condition for the members with shear reinforcement. This is a picture from the book which I wrote, and this is a derivation of the formulas which are in Eurocode, valid for shear. We have a shear force acting in the element, and the element resists by the stresses in the concrete in compression, by, of course, forces in the stirrups, and also, which is not very usual, I would say, by the force in longitudinal reinforcement. You can see that we have actually derived here three equilibrium conditions, which are not in Eurocode. I just wanted to make sure that we understand the principle. And from these equilibrium conditions, we can derive the formulas which are in Eurocode, and those are this one. This is the formula for the maximum shear force due to the resistance of the strut. This is due to the resistance of the stirrups. But here you have an additional condition for longitudinal reinforcement. Can you see these two forces? The shear, pure shear, will develop tension in longitudinal reinforcement, which we did not realize before. There were some provisions in old codes which took care about it, but actually it was not possible to derive it in this way. If we go further, we have additional unknown, and this is the theta angle of that diagonal. Actually, we have three equations and four unknowns, if you see. And this can be done, or this can be solved by three methods. Either Eurocode allows you to choose the angle from 21.8 to 45 degrees. The second possibility is that you model it in the way that it reaches, you want to reach the compressive strength in concrete strut, which means that you want to use the material which you already designed in the cross-section. Other possibility is that you want to reach yield strength in longitudinal and transverse reinforcement. The first one is simple, you can just select one of those, but then you do not probably get the optimum solution. The second one, you have to discuss or you have to analyze these failure modes and you can get optimum angle. Actually, we did it in the program and we can analyze, and you can see it in the picture, what is the optimum angle of this strut, and then you improve the economy. And actually, default angle in Eurocode is 45 degrees, and here we have, I do not remember, 31. So this was after the optimization which program gives you how it is optimized. Now I wanted to show the picture from SNP, and you can see, you will see the comparison of the formulas from Eurocode, which I have already explained, and the formulas in SNP. So first one is the strength of the compression strut. You see, of course, completely different formula, but there is analogy. There is analogy between those two. Second one is again the strength which is coming from the shear reinforcement, from stirrups and probably benta bars. Do you use benta bars in your country? Do you know what benta bars are? Call it hoop in Czech. This one. I just so we already implemented these benta bars, even if there is no direct method in Eurocode. We did it, but I cannot mention it here. Actually, we can agree with our local distributor BIM Solution here that we can invite you for some online webinar, let's say in 2-3 weeks, and I can explain more, or we can have these webinars regularly, but it will be only in English. Last what I wanted, not last, but one before last, is that in Eurocode you can see there is no shear force transmitted by concrete in compression. That was a bit surprise also for me, because in our old codes we had it similarly as it is in SNP code, which gives you a little bit lower values in some cases. So this component of the strength is not in Eurocode. And last one, I was thinking how to compare this formula with the formula which is in SNP, and finally I realized that probably this longitudinal force or force in longitudinal reinforcement can be calculated in some way from this condition for moment resistance, which is in SNP code. So I haven't done any comparative calculations, but I think SNP code guaranteed some level of longitudinal reinforcement through this condition. Then we have a torsion. Again, without any comment, there are equilibrium equations here, and Eurocode defines from these equilibrium equations, which are not in Eurocode, you can calculate or you can derive these formulas which are in Eurocode. Actually, every cross-section is calculated as equivalent thin-walled section. They use breadth formula. I've been tested the principle, and we transfer the torsion by longitudinal reinforcement, stirrups, and concrete. This is very similar to the one which is in SNP code. This is unformatted, sorry. For this old SNP code, there is only condition for principal stresses, but for new one, yeah, now it is there. So for new one, you know that there was a spatial model of inclined section. 3 edges of the section were in tension, and one was in compression. And the calculation is a little bit similar to the one which is in Eurocode, but it's not completely the same. But you again calculate the resistance of strut and torsional moment transmitted by reinforcement, which is similar to Eurocode. What we do in the program is that we calculate this equivalent involved section, as I mentioned, automatically based on the stirrups which are marked by the user, and we can calculate it automatically. About the interaction, there is quite detailed interaction of shear and torsion in Eurocode. You can see this is the interaction related to concrete resistance without the reinforcement, and this one is the resistance of the strut in compression. Also, we can have formulas for stirrup reinforcement. In SNP code, sorry for this, we have formulas for shear and torsion, and formulas for torsion and flexure. There is no such formula in Eurocode, but actually the model which is for shear and torsion in Eurocode allows you to respect the interaction of all internal forces. I will explain only the simple one, which is the interaction of shear force and bending moment. You see that I explained in the previous pictures that due to the shear you have tensile forces in both, we call it stringers. This reinforcement, longitudinal reinforcement, is a stringer. It is uniaxially loaded by this force. For bending moment we have one tensile and one compression force, and if you add this plus this, you get the real force in the bottom reinforcement, which you can check. And similarly, we do it differently in the code, in the program. But similarly, you can have the interaction of all components of internal forces. I can explain it during some webinar. There is also, and also Gattis mentioned this, the strut and tie model available in Eurocode or usable according to Eurocode. And we developed first of the details, and this is strut and tie model for brackets and corbels. Of course, the reinforcement is automized, and you can check all these details. Now we go to serviceability limit states. There is a big chapter about stress limitation in concrete, non-pre-stress and pre-stress reinforcement, also crack width, and new decompression condition of pre-stress concrete. I will explain this decompression later. What is very new, at least compared to our codes, is this status. You have to check if your stress is less than tensile strength in concrete, and if not, then you have to disregard the concrete in tension. So you have linear stress in compression in concrete and no stress in tension, even if serviceability limit stays. That was not the case in our previous codes, and it makes it a little bit complicated. It is not N over W, M over W, it is nonlinear solution. Actually, this distribution used to be an assumption for the analysis in, we call it classical theory in our old Czech codes. Now we go to the conditions for crack control. You see the crack width for standard Eurocode, but there is also this new decompression condition. Actually, this is, I do not know why they call it decompression, because this is something different, some feature which is in the literature, in the American and English literature, is not called decompression. Decompression state is something else. But they call it in Eurocode, I do not know why, and it is actually the compression reserve. You have to make sure that around your pre-stressed reinforcement, you have compression in both sides, at least 25 millimeters and at least 100 millimeters for bridges. So it is, if we speak about decompression according to Eurocode, it means that it is a compression reserve. Crack width, I give you this formula only. This is completely different than in SNP code. You have to calculate the distance of the cracks, and then you have to calculate or subtract the strain in steel minus strain, mean strain, average strain in concrete. There is quite a complicated formula, you can derive it. It's not completely empirical. This one is empirical, and this one is also a problem. In standard Eurocode, sometimes you get very, very big cracks. Depends on the situation due to this effect. And what I learned was that Germany and France improved this crack width calculation, even if it was not allowed. Actually, countries like Czech Republic, Slovakia, Poland, maybe also Austria, they respect everything which was in Eurocode, and we change only the factors. If we go to Germany or France, they change everything. So it is completely different code. It is actually not so that they have same codes as we do. So this is an improvement. If I have to speak about calculation deflection, we have no time for it, but I just wanted to say that we respect, or Eurocode respects, the effect which is called tension stiffening. Tension stiffening effect. This is the effect of this shaded area. Actually, Eurocode distinguishes two states. State 1, which is uncracked, and state 2, which is completely destroyed by cracks. And we have one formula. This is empirical formula. The ratio of this and this is equal to this, and the rest of those two formulas, this is derived from the homotopy of the triangles in this picture. So you can see it in 1 minute. If you see the picture, it is okay. But if you substitute those formulas into these well-known formulas for strains, then you get after some derivation, you get such formula for any quantity like deflection or stiffness or curvature or these things. And you see that you interpolate between state 1, uncracked, and state 2, which is completely cracked. And the interpolation factor is this zeta. So this is the way how they do it. In the program, we calculate bending moments, and then after you calculate, or the program calculates the stiffness, then we get higher deflection due to the nonlinearity, due to the cracks. Last but not least is this crack width calculation for liquid retaining and containment structures. You have to classify the tightness, and based on the tightness, you calculate the check of depth of compression zone. I finally decided to show you some pictures from the study which I did some 2-3 years ago according to these SLS conditions. I do not know if you really use these serviceability conditions in your practice. Do you? Do you always use it? Because some of our users, okay, I can see. Some users in our country, they both are programmed, and they even did not input the forces into SLS conditions. And finally, it happened that everything was okay, because there was 0, 0, 0. And then another user came, and he found that everything had to be recalculated, because the reinforcement was not enough. They had to increase the depth of the cross-section and like this. So we realized that some people thought that it is groundless complication of the design. The other people say that this is an essential part of design, because what we learned finally, it is governing in most cases. So you do not even need to calculate the structure for ULS, but you do need it to calculate it according to SLS, according to Eurocode. I will show you some pictures. What I did was the study, sensitivity analysis of such pre-stressed beam. That was a 1.4 meters roof girder. You see that it was quite practical, completely reinforced as it is necessary. It is again pictures, or these are the pictures from our program. I did it in our program, and I made these alternatives or variants of the analysis. First one was, this is an exposure class. Again, it is not visible in this PowerPoint. So we have XD1 means that there are chlorides. Okay, you have the exposure to chlorides, and you can have a corrosion because of chlorides. Here you have XC. This is because of carbonation, corrosion. This means that you have moderate humidity, but chlorides, and here we have carbonation, permanently wet or permanently dry, and here this is cyclic, dry and wet, and so. Okay, then the rest, what we changed or studied was these factors. Those are the factors for the combinations. If you have SLS combinations, you have psi factors based on the category of building. I will mention the category later. Okay, and last one, we change these R inf and R sub factors. Those factors are used to multiply the pre-stressing force in case of SLS in serviceability limit states calculations. And it is such big that for post-tensioning, for example, it is 10% less and 10% up to 20% scattered, which is, for me, it is unbelievable and unacceptable and uneconomic, actually. So we did it. We had the cases with 6, 7, 8, and 9 strands in the cross-section, and in total 9 times 4, 36 calculations of that structure. Those are only some pictures of ultimate limit state in flexure. You see at the time, this is equivalent age, okay? Equivalent age, not the real one, because there is a heating and speeding up of the hardening and so on. So this is at the time of pre-stressing. You see that higher stress is in the bottom fibers, higher compressive stress. Then at 28 days, we already have some load on it, live load, or we now call it variable load, or and you see this parabolic rectangular, we have already reached the plastic branch, so it is at the ultimate limit state for six strands. And this is in 100 years, it changed because of the long-term losses. And here we have the same picture, 100 years, but for 9 strands. You see that there is no plastic behavior, nothing. The section is not used fully for ultimate limit state. And that is what I was scared about when I noticed the reformatting. What shall I do now? So this should be a picture showing, I'm very sorry for it. I should have gone through it. I did not realize it. So these are the factors. By the way, we can provide you PDF of the presentation and the pictures will be correct, okay? So if anybody wants, or maybe you can send it to anyone. Yeah, okay, sorry about it. I just wanted to show that maybe I will skip it because it's really terrible, the picture. I will only conclude finally. So this will be same. This is a category of factors and this is influence of exposure classes. I'm happy that conclusions are correct. The pictures which you didn't see should show you that SLS conditions appear governing, so they were critical for all cases, It was even so that only 75% of ultimate limit state capacity was used if you designed it for SLS. So if you say, I will have 100% utilization for serviceability, then you get only 75% utilization for ultimate limit state in flexure. I am speaking about flexure, okay? In flexure. So, on the other hand, if you design it for ultimate limit state, if you say, I design only ultimate limit state, then all your beams would be unsatisfactory for mainly decompression condition. This is actually what I explained, required distance of pre-stressing reinforcement from tensile zone. This is the compression reserve. I know that one of the possible critical factors was the condition for creep, creep linearity, but this was really critical. And you can improve this situation by changing R sub R inf. Frankly, now I do not know if you changed it in your annex, national annex. Maybe we can ask Eric or Yanis or Gatis, so I do not know. But You see this Belgium, Netherlands, Singapore. Singapore has a Eurocode too. We have it implemented, and they use 1.0. Standard uses 0.9, 1.1. It is even possible to use 1.0, and then you improve the situation, you make it more economic, but you need the measurements of pre-stressing force, which we do usually in our country, so it should not be a problem. Last several pictures are about the program itself. This is a list of all ultimate limit state calculations which we provide. You can see that we have composite section concrete to concrete, so you can have pre-tangent, for example, or post-tangent beam with cast in place composite slab. Similarly here, this is a bridge, and this is the floor structure garage in Netherlands. Stability limit states, all the limit states which we have. This is additional brittle failure check, which is in Eurocode. I didn't have the time to speak about, sorry about that. And this is a range of application of idea Statica. Maybe I should repeat what Martin said when we was speaking about steel joints. Our idea Statica is focused on the design of members, cross-sections, and details. We do not directly compete to such programs. We even collaborate. We implemented pre-stressing into RFM. It is called RF tendon. In our applications, idea Statica, we can analyze, you can see prefabricated bridges, pre-tangent, post-tangent, non-pre-stressed, any type of prefabricated beams, I wanted to say, sorry about that. Or you can use it for design strips of post-tangent slabs. You have a slab, post-tangent slab, and you select a column strip, and you calculate, you design the tendons in this strip. Or bridge piers, or of course some types of bridges, like bridges cast in place into false work, or continuous bridges with composite concrete slab, which I already explained, or I wanted to explain. Again, completely different what I wanted, but I just wanted to mention once again the possibility of online webinar. And of course, you can contact us after the seminar on the desk, which is at the end, behind you, and we can discuss what you are interested in or what I haven't mentioned. Thank you very much, and again, terribly apologize for the problems with the PowerPoint. Next time it will be better.
Thank you, Jaroslav. It was a nice presentation. Nu, principā mums esam nonākuši, laikam, jautājumu un atbildu tādai sekcijai. Tā viņš šoreiz nosauka. Varbūt, teiksim tā, ja kādam ir jautājumi, varbūt kāds pacēl roku, tad mēs mēģināsim viņu atbildēt. Un saules spīd acīt. Jā, lūdzu.
Give microphone.
Okay, the question was, the software you showed, is it possible only to calculate, or is it possible to model as well?
Actually, if you mean by modeling that we have the possibility to produce drawings and to model the geometry of complex 3D structure, then no. But on the other hand, what we do, we have, of course, our input and our modeling. If you have 3D beam with various cross-section, with haunches, changes of the cross-section, you can, of course, model it in our standalone program. Also, the steel connections, you model it in the way which you cannot model in other software. You can really make such joint in 10 minutes to input it, and it speaks, I would say, your language, because there are manufacturing operations. So yes and no. Yes, for the applications which we really support, beams, cross-sections, and details. No for complex 3D structures. Okay?
Is it possible to make shop drawings?
No, not directly. We can export the reinforcement which you saw in this presentation. You can export to DXF. You can export to DXF and use it as a draft drawing. But currently we can cooperate. Steel connections can cooperate with Tekla, Advanced Steel, robot, of course RFM, SCIA possibly, but this is not very good. Axis VM and Concrete is able to cooperate with all of them except of Tekla and Advanced Steel, and we will work definitely on Tekla. Okay, so we will be able to read the data from Tekla to design reinforcement and pre-stressed tendons and to put it back to Tekla. But it is not currently in the release. Okay.
Paldies!
Thank you.